Good afternoon, everybody, and welcome to today's ACR event. This is the panel discussion on applications of AI in research computing. We have 6 panelists. All of them are the newly appointed IDRE Fellows 2024-25. They are Dr. Barbara Doriga from MAE, Dr. Claire Schollaert from Environment Health Sciences, Dr. Eulanca from Radiation Oncology, Dr. Zhou from Mathematics, Dr. Hesam Soleimani from Civil Engineering, and Dr. Tsukasa Yoshinaga from Head and Neck Surgery. So we are recording this session, which will be available at some point on our YouTube channel. And I think without much ado, let's start. So I will start with Dr. Barbara Doriga.
Sounds good. Thank you for the introduction. So my name is Barbara. I work with Sam Tyra. I'm the mechanical and aerospace engineering department. And the title of my project is Optimal Airfoil Design for Unsteady Aerodynamic Flows Using Machine Learning. But let me start by motivating the problem that we're interested in. Small aircraft, and in particular unmanned air vehicles, have been, in the past decade, become very popular for several reasons. Some of them include logistics. Some applications include logistics, more simple ones like deliveries, transportation in general. But there are other more crucial applications like weather measurements in extreme weather conditions or civilian rescue that could be very beneficial to us as engineers. But the problem with these vehicles is that because of their small scale, they're exposed to very strong and very unsteady conditions, aerodynamic conditions, even in urban settings. So if you can see the figure on the right, these are very unsteady conditions, unfortunately. And so what we would like to do with our research is answer the question of what is the optimal airfoil design for these small scale vehicles that can better equip them to contend with these strong and unpredictable aerodynamic conditions. And so what we propose is a 3-step process. And so the first step would be to collect and form a library of different high fidelity simulations where we look at different airfoil geometries and different aerodynamic conditions. Once we have this library, then we go to step 2, which is we train a variational autoencoder so that we can find a reduced order model, a nonlinear reduced order model that can capture both the geometry of our airfoil, but also the dynamics of these aerodynamic encounters. And the way we do this is by trying to reconstruct this library that we generated at first. But essentially, once we determine the variables in this latent space, what we obtain is a manifold, a nonlinear submanifold that we can use for step 3. And so once we have this manifold, for one initial condition, we can use some sort of gradient-based optimization method so that traveling through this manifold, we can find the optimal geometry. And so the idea is that we would start with an initial geometry like this and find an optimized geometry. And so to us, what we're trying to do is, like I said, find these optimal airfoil that can mitigate the effect of the gust. And so for step 1, which is, I started last summer, so we're still finishing up step 1. But the idea is that we create a library with high fidelity simulations with different airfoils. And so our parameter space is big. It's 6 parameters. The first 3 are external conditions. So the way we generate these unsteady conditions is by throwing a vortical gust. It's a vortex. Then with where we can adjust the strength of this vortex, which we call the gust ratio G. We can adjust the initial position of this gust, which is also very relevant, and the angle of attack of the airfoil, which is the angle between the chord of the airfoil and the oncoming flow. And then specifically for the airfoil, we also have 3 parameters for the thickness, the camber, which is the curvature, and the position of maximum camber. And so the idea is that if we do a sweep through all of these 6 parameters, we can create a very rich library of different airfoil geometries that will allow us to find the optimal design once we build our autoencoder. And so this library has turned out to be so rich that we are just writing a paper on the results that we have found from this library. And there are 2 things that I wanted to mention about this library that we built. When we say that we're trying to find the optimal airfoil, what we're trying to do is mitigate the fluctuations in the lift. So the lift is the force in the vertical direction that's sustaining our vehicle. And when we throw a gust onto the airfoil, what we see is that there's a peak in the lift and then it drops. And here I'm showing 3 examples for 3 different airfoils, but what we're trying to do is reduce the magnitude of these 2 peaks. And sweeping through different gas ratios or strengths, different cambers, thicknesses, and all that, the main 2 findings that we wanted to bring up is, first one, the curvature of the airfoil is not making that big of a difference. And the second one is that the thickness is going to be our main parameter of interest. I'm just adding 2 plots just to give everybody an idea, but essentially I'm plotting the lift for different airfoils. The blue ones are the thinner ones, thicker ones are the red ones. As you can see here, these are the lift coefficients before I even introduced the gust. There's a big difference between the thickness, but as we change the camber, there's not really a big difference. If you compare the blue curves, there's not really a big difference. And even if we introduce a gust, there's not a big difference between the blue curves, orange curves, and so forth. But what's interesting is that here I'm showing the effect of the thickness. There's a big difference in the lift that we observe as we change the thickness. In this lift, it's actually a linear function of the thickness, which this has been reported in the literature, but it was nice to see how these figures came out so clean. And so this is where we're at right now. We're writing a paper, like I said, in this library about this library of high fidelity simulations. But the next step, hopefully in the next semester, would be to build this autoencoder and then eventually find the optimal airfoil design. I hope that was clear, but I would be happy to answer any questions. Thank you.
Let's wait for the end of the presentations for any questions. So hold on to those, or if you want, you can put it in the chat and we will take it later on. Thank you.
Thank you.
The next one is Dr. Claire Schollaert. Claire.
Okay, let me just bring these slides up. Hopefully those look okay. Okay, so thank you again. My name's Claire. I'm a postdoc in the Environmental Health Department in the School of Public Health. I study wildfire and forest management impacts on wildfire smoke exposures and health, with a particular focus on environmental justice communities that might be disproportionately impacted by wildfire smoke. I'm going to spend my short amount of time today not necessarily talking about my research specifically like Barbara, but more broadly highlighting the challenges that we face in trying to quantify smoke that people are actually exposed to, and the role that machine learning approaches can play in alleviating some of those challenges for us. I think many of us across the West Coast, and particularly in California, are acutely aware of the impacts of wildfire smoke on air quality. There are several known health effects of being exposed to wildfire smoke, with some of the more long-term serious health effects being things like all-cause mortality, as well as respiratory-related mortality and morbidities, so things like asthma and COPD. We've also seen an association between cardiovascular outcomes and smoke exposure. And then there have been some studies documenting associations between smoke exposure and birth outcomes, so things like preterm birth and low birth weight, as well as some more recent work examining the impact of smoke on mental health outcomes and some other cognitive disorders, with some very recent work coming out of the University of Washington linking wildfire smoke with Alzheimer's disease, for example. And so our understanding of the health impacts of smoke exposure all stems from epidemiological studies, which all require some measure of exposure. And we've historically really relied on ground monitoring networks for both a research and a practice perspective. I have a screenshot here of the AirNow platform that many of you may be familiar with if you ever check air quality in a region before you go outside during the smoke season. But this map is just showing the distribution of regulatory ground monitors across California and Nevada as an example. They're really great, these monitors, at providing air quality pollution information, or air pollution information, sorry, at a very single location at fairly fine temporal resolutions, but they can only measure total pollutant concentrations and not source specific contributions, meaning it can be really hard to piece apart what pollution is coming from wildfires versus other sources like traffic-related air pollution, energy production, et cetera. You'll also notice that while there's pretty decent spatial coverage in more urban areas, these monitors are otherwise really sparsely distributed, particularly in rural areas and areas where there are a lot of fires, with the biggest implication of that being exposure misclassification, so not having a good grasp on how much smoke people are actually exposed to, particularly areas with complex meteorology and complex terrain. Alternatives or supplementary exposure monitoring tools include temporary monitors, low-cost sensors, wearable sensors. These are all tools that still measure pollutants in very specific locations, but can increase coverage depending on how and where you deploy them. And then we move into tools like dispersion models and satellite data sources, which can provide a bit better spatial coverage, but still not perfect. Satellites in particular are often subject to missing data issues due to things like cloud cover, mountainous terrain, high surface albedo issues, etc. And the temporal resolution of satellite observations are also limited to flyover times of each individual satellite. So this is all to say that there are a variety of different approaches to characterize wildfire smoke, all with their own pitfalls that contribute to spatial and temporal uncertainties. But some recent studies, however, have started to utilize some machine learning approaches that allow them to harness inputs from all of these different data sources, plus some other information related to things like meteorology, topography, etc. So the first potential limitation that machine learning approaches can address is the spatial coverage issue. I mentioned that this is a major issue when using ground monitoring data, but also when using satellite observations with a lot of missing values. So this is an example from a paper from a group up in Washington who used two different machine learning approaches to address gaps in aerosol optical depth observations from the MIAC sensor on board the Terra and Aqua NASA satellites. Aerosol optical depth, or AOD, is a vertical measurement we can get from satellites about the amount of aerosol in a column of air between the Earth's surface and the sensor itself. So AOD measurements can be statistically related to air pollution concentrations and can thus give us an idea about smoke exposures during wildfire events. But as I mentioned before, missing values are still an issue, and the map on the top left panel kind of shows that, where you have AOD observations from the MIAC sensor over the Northwest, with all that white space representing missing values. The next figure on the top right is showing aerosol optical depth that has been modeled using a chemical transport model called CMAC. So that model ultimately takes pollutant emissions from the surface and tracks how they're transported or dispersed to the atmosphere in order to try to recreate that AOD measure with better spatial coverage. And you'll see in the top left corner of that map, we get a correlation coefficient of about 0.7 when compared to the direct AOD measurements we get from the satellite sensor. So not bad, but not amazing performance. And then this research group then went on to take these AOD measurements they got from the chemical transport model and using a couple different machine learning approaches to adjust the modeled AOD estimates using ground observations from station data and other meteorological inputs. On the bottom left, you can see the results from the random forest approach. And then on the right, you can see results from a generalized boosting model. And both dramatically improve spatial coverage relative to satellite observations and also perform really well with R values of 0.96 for both of those approaches compared to satellite observations. And I'll wrap up by just highlighting one other application which can address the temporal as well as the spatial limitations that come with some of our other exposure assessment methods, which often only allow us to look at daily air pollution averages instead of sub-daily, which is really much more useful to us in thinking about human exposure and health impacts. So this study from British Columbia leveraged ground monitoring stations around the Vancouver metro area, which provided hourly air pollution measurements from very specific locations and extended that information from those stationary monitors along with fire activity data, meteorological and topographical inputs to estimate hourly air pollution concentrations in all of the populated regions within this airshed using a random forest approach. So on the left-hand column here, you can see the modeled particulate concentration estimates from the random forest model in gray relative to the observed concentrations shown in the black line for each of these three monitoring locations in this region. And then the right column is showing a few of the sub-daily time snapshots during this particular smoke event, showing how they were able to generate an air pollution surface across this region, extending beyond just where there are those singular monitoring stations, which are shown in those numbered circles using this data fusion approach. So I will stop there because I know I'm very much out of time, but I really just wanted to highlight a few of the ways that machine learning approaches can help us overcome some of the spatial and temporal limitations in the wildfire smoke exposure assessment world. And I'm happy to chat or answer any questions once we get to the panel section.
Thank you, Claire. Next one is Dr. Eulanca Liu.
All right. Hi, everybody. My name is Eulanca Liu. I'm a postdoctoral fellow in the Zhou lab in radiation oncology here at UCLA. I'm also a radiation oncology resident physician currently in my 4th year. So I am doing a variety of different projects within the Zhou lab that leverage AI and machine learning. But for this talk, I wanted to talk about a recent project I've been working on leveraging LLMs for accurate differentiation between 2 conditions that affect our patients who have brain metastases, so radiation necrosis or tumor progression. And I'll dive a little bit more into detail. So brain metastases occur when cancer cells break away from a primary tumor in a patient's body. They travel through the blood or lymph, and then they form new tumors in distant tissues. One of the areas of preferred metastasis in many different types of primary cancers are metastases in the brain, and it affects more than 20% of all cancer patients. So when a patient does develop brain metastases, they have several treatment options. They can do surgery, which can be fairly morbid and is usually reserved for metastases that are very large and causing significant neurologic symptoms that require urgent decompression. They can try systemic treatments, but not all medications cross the blood-brain barrier. So this can be a problem. And so one of the mainstays is something that we offer in radiation oncology, which is stereotactic radiosurgery, where we're directing high beams of photons or X-rays at these brain metastases in 1 to 5 fractions, and we're able to with a very high rate of disease control. So one thing that does happen as a result of stereotactic radiosurgery, or SRS, is radiation necrosis. It's a frequent adverse event, and it's basically an inflammatory condition caused by late normal tissue cell death. Treatment for this can include things like steroids, systemic treatments like bevacizumab, or minimally invasive surgical procedures. The reason this is important is that radiation necrosis, when we're looking to diagnose it on standard MRI imaging, can be very difficult to distinguish from brain metastases that have actually recurred or progressed. So what you typically see on a MRI scan of radiation necrosis is you can see some increase perhaps in the size of the tumor itself, as well as surrounding edema. But that can also occur if you have a brain metastasis that's actually growing. These aren't the best photos, I apologize, but essentially on MRI with just standard anatomical imaging, T1 weighted post contrast, it can be very difficult to distinguish. Patients also refer very similar symptoms. So they'll have neurologic symptoms, they'll have headache, dizziness, nausea. And we are, it's very important to us to distinguish between these 2 conditions, because one is, cancer progression, where you have to think about different types of treatment options for the cancer, versus the other one is controlling just inflammation. So in our project, what we wanted to do was kind of study the temporal evolution of radiation necrosis in patients and to determine whether or not there's any correlation with response to SRS, depending on the type of primary tumor, what kind of treatment they received. And to do that, we wanted to retrospectively analyze a large quantity of MRI radiology reports where our neuroradiologists were able to differentiate between the 2 in their reports. And so we wanted to use a large language model to basically combined with prompt engineering to develop an automated scoring system to classify the concern for radiation necrosis, so that we can then move into analyzing this very, very large set of data of thousands of MRI images. So in our pilot study, we utilized a smaller set, 107 T1 weighted MRI post-contrast reports. We ran inference on the 70 billion parameter Llama 3 model and utilized specific prompts designed to capture the nuanced language and diagnostic criteria related to either radiation necrosis or tumor progression. I then calculated the agreement by similarity between the LLM calculated classification and a physician score. And these are just examples of some of the impressions you may see in a radiology report where sometimes the radiologist is very definitive. They say findings are most compatible with radiation necrosis. And so the LLM is able to score this as very high confidence of evidence of radiation necrosis, which is compatible with the human rater as well. Other impressions are a little bit more ambiguous, and so they say things like progressive areas of internal enhancement necrosis likely reflect post-treatment change, but they don't outright say radiation necrosis in their impression, and so the LLM is unable to classify this as radiation necrosis in concordance with the human rater. So I did an initial first pass with Llama 3 and didn't really give it any information on what radiation necrosis or tumor progression was, and saw an accuracy around 43.4% and a agreement coefficient of which is AC1 of around 0.41. AC1 is useful in assessing how closely different raters agree on categorizing items. So it considers both observed agreement as well as expected agreement and adjusts for agreement purely by chance. Then on a subsequent passes with prompt engineering, so essentially being able to give feedback to the model on types of phrases or findings to categorize into each of these conditions, we were able to see an improvement in accuracy to 72% with an AC1 value of 0.719. So we were able to see with an iterative effort, basically improving machine learning large language model performance on this classification task. And while the first pass performance has demonstrated relatively low accuracy, we were able to, with prompt engineering adjustments, refine the definitions and distinctions between the clinical conditions and increased accuracy to 72% with an improved AC1. And so I think this just shows kind of preliminarily a very early on progress in targeting language and clear examples and prompts to help the model better predict and interpret the reports to closely align with human classification. So really what's most important here is our future direction. So we want to run all of our available radiology reports, which we have kind of a collated data set of around 2,000 to 3,000 reports through Llama 3. We also want to test the newer 70 billion parameter Llama 3.1 model. But in addition to all this, we want to be able to include all the patient's progress notes, surgical notes, pathology data, and medications into the LLM because this will provide it with additional context. It'll be able to see the timeline of when a patient was diagnosed, what types of treatments were offered, and then whether or not the patient improved. And this will be able to help us better understand as well, again, that kind of temporal evolution of radiation necrosis. So we'll be able to basically get a more comprehensive view of the evolution of a patient's brain metastasis post-SRS. So I just want to say thank you. I appreciate our, the privilege of presenting to Asia and my lab as well, Dr. Sajani's lab. I'll pass it on to the next panelist.
Next one is Zhou from mathematics.
Hi, I'm not a co-host right now. Can you let me share the screen? Can you let me share the screen? Oh, okay. Now I can share. Hi, everyone. I'm Mo from the Math Department, and different from the previous speakers, I will not talk about my research project because honestly speaking, it's super technical and probably only a very few people can how these machine learning or AI things are become that popular in today's research. And I would like to share my thought in two aspects. The first one is the strong expressive capability of neural network. And the second one is the robust algorithms from different machine learning areas, such as reinforcement learning. So let me mention the first one. A strong expressive capability of neural networks. Actually, we have seen a lot of empirical successes with different structure of neural networks. We have, for example, in 2016, the AlphaGo beat Shadow Lee, one of the top Go players in the world, and their team were using a search Monte Carlo tree and the structure of deep neural network to build their AlphaGo model. And the second one is the generative adversarial model, which has been widely used in image generation. And the third example is the ChatGPT, where we use the structure of transformer to form large language model. And of course, we can also use transformer to generate image and so on. Anyway, I would like to mention that different neural network structures, all of them have very strong representation power, and it has the capability to represent the function that you want in your specific research. And since I'm a mathematician, I would like to dig a little bit detail into how it works. I will just take a very simple toy example, which is just a Laplace equation in d dimensions. Traditionally, if people want to solve such a problem, either in engineering or math, or in computational mathematics, we will partition the total domain into grid and assign a value on each grid, or using finite element method to give us a linear basis. However, this method only works well in low dimensions. When the dimension becomes high, the computational cost will grow exponentially with respect to this dimension d, which causes the curse of dimensionality. And in comparison, the neural network parameterizes the function you want using the parameters weight W and bias B, and use the composition of a bunch of linear transform and nonlinear activation to to formulate your parameterization. And as a result, the complexity for the traditional method, when you compute such a problem or your problem, the cost will scale exponentially with respect to the dimension. For example, if you want an accuracy of order epsilon, then you will need 1 over epsilon to the d order computation. So as a simple example, you let epsilon to be 1%, which is 0.01, and the d become 10. Then the cost will be not affordable if you compute it in the naive or traditional way. However, we have observed many empirical success that if we use neural network to compute such problems, although there is still some error, we are able to compute high dimensional problems with a relatively reasonable result. Okay, so for the in terms of complexity, neural network has reduced the cost, and also another thing that is different is the solver. Traditionally, usually when we formulate a problem, we just directly discretize the problem we have in the continuous space and solve it directly. Well, for the modern machine learning or AI method, we usually construct a loss function and then minimize it. And this also incentive the development of different optimization techniques. And this is for the strong expressibility of the neural network. And secondly, I would like to mention that in addition to the strong expressive capability of neural network, machine learning also provides us a lot of flexible and robust algorithm while solving the problems we face. And what I would like to mention today is called reinforcement learning, which is a subclass of machine learning. And reinforcement learning is a technique that teaches software or agents to make decisions to achieve optimal results. And here is the model. We have an environment and an agent. The agent wants to maximize its reward. And the core model is the Markov decision process. That is, the agent starts with some initial state denoted by S0, and then it makes action within a certain action space. And let's denote the first action by A0. After taking an action, the agent moves to the next state, denoted by S1, and it also receives a reward, denoted by R1. Given the new reward and new state, the agent makes another action, denoted by A1, and get a new reward R2 and S2, and so on. The goal of this model is to maximize the cumulative reward, a discounted cumulative reward, and to design the best action or policy in order to maximize the cumulative reward. And through inside this machine learning field, one of the very common technique is very common framework to solve this problem is called actor-critic. It's called the actor-critic method. This is what I'm doing, but I just have one word to describe my work. My work is just to apply this actor-critic work from actor-critic framework from reinforcement learning to solve stochastic optimal control problem. The technical details are very complicated, so I'm not going to present it today, but I would like to share the idea of this actor-critic framework because perhaps it's useful in the more general research. And starting with an environment similar as the previous model, an agent make an action denoted by 0, and after making this action, the agent gets a new state and a reward here. And then using this new state and reward, the agent is going to compute a quantity called value function. And this value function is where this critic refers to. It is the expected cost or reward with respect to a certain policy. And this value function will tell the agent how good our current policy is, which will be helpful in the future to improve the policy or improve how do we take action. And this value function is usually computed through a quantity called temporal difference. And after computing this value function, we can evaluate whether it's good or not, because the value function is just the expected cost or reward. So we can use that to try to improve the strategy that we are using to take action. This is what the actor refers to. The actor refers to a control or policy, and it decides what action we should take. And the procedure of and in the actor, we usually do a procedure called policy improvement in order to take a better policy. And in the actor critic framework, we can see that the critic and the actor part are trying to help each other in order to achieve the optimal policy. And I have been applying this framework from reinforcement learning to my research on stochastic optimal control problem, both numerically and theoretically. But this is not the topic for today. For today, this is just what I would like to share. And thank you. Let me come back. Strong expressive capability and robust algorithm. That's why reinforcement learning, machine learning are helpful in today's research. Thank you.
Thank you, Mo. Next one is Dr. Hesam Soleimani.
Oh, yes, sure. So good afternoon, everyone. Hopefully everyone is doing pretty fine. So I'm gonna talk about like the previous presenters, I'm not gonna go over like the detailed of my research. Probably I'm gonna do that for the next presentations for the IDRE. So today I'm gonna talk about more like the application of AI in civil engineering methods. So to have like an overview of what I'm going to talk about, I'm going to divide the methods in civil engineering into 3 parts. So the methods that already use some data-driven approaches, the ones that are using expert knowledge, and the ones that are physics-based. So I'm going to describe how AI came in and like changes this field or what contribution it could offer, because at the end I'm going to make some observations out there. So I'm going to go, for example, for the first example, which is a structural health monitoring, which is a data-driven approach. So in the data-driven approach, people were actually using AI, more simpler or traditional types of AI. Like, for example, they were using random trees, they were using like gradient boosting machines and other things. But what they came in and that I'm going to be talking about is how the deep learning actually changed these fields. So in the field of structural health monitoring, all we have are some structures, and on those structures we have installed some sensors. So from those sensors, we get very high dimensional and very noisy data. So actually working with this data is pretty hard with like normal models, like, I don't know, like clustering or like support vector machines and others. So they cannot solve this problem because this problem is very hard. But deep learning can come in and actually solve this problem. So now not only we can do a structured monitoring for each of these structures pretty easily, but we can also transfer this knowledge across different systems. So for example, we can have a rotating machines and we can have a building and we can use and train and develop some models that work for both of them. So this is how the deep learning is actually revolutionizing the field. So the second one is a signal reconstruction. So we have signals from sensors, from vehicles, from many different devices. So at some points, I mean, the signals might be corrupted. I mean, maybe the data is lost or there's some very noisy situations. And if we look into the literature about what people are currently using, I mean, this is a data-driven model. I mean, people were using autoregressive models and other machine learning models. But now if you look into the literature and some review papers, we can see that deep learning models are dominating the fields like CNNs, GANs, and like some old models like Kalman filtering or I, I mean, dimensionality reduction, I should find it. I mean, all those models are no longer usable. I mean, the deep learning can give us so much versatility that we do not need those old models anymore. So the third example is actually traffic demand prediction. So for example, here is a picture of like the traffic demand on like 3 different days. So the very hard part of these classifications or actually predictions are where the surges occur. So for example, we have some surges here. And the current research has found that the traditional models are completely beaten by deep neural networks. I mean, specifically, they work with very nonlinear and hard to predict data. So actually, identification of these surges are much easier for deep learning models. And the other example is forecasting air pollutions. I mean, so there's some terminology here. So some people may call like simpler artificial intelligence methods like traditional statistical models or methods or others. But here, for example, in this paper, they're just calling artificial intelligence models a deep learning. And what, again, they found that is that the deep learning models are already beating the traditional models. And especially if we make some hybrid models out of them, that we give the deep learning and artificial intelligence models to do the feature selection and the feature extraction because they're pretty good at that. And then give it to the traditional statistical models, that would work much better. So now we go to the expert knowledge part. So for the expert knowledge, or what I can call human in the loop, I mean, we need to have some inputs from the user, from the human. So we can see how that's, inclusion of the AI into the civil engineering methods could replace the expert knowledge. So one of those examples is larger scale hazard simulation. So for the phases of disaster management as a result of hazards, we have mitigation, preparedness, response, and recovery. And for the first 2 stages with mitigation and preparedness, we need to have detailed information of the structures, of the infrastructures, of the people, of many things, to know how to simulate and to understand the problems, to mitigate them and be prepared for hazards. So for example, we have tax data, we have census data, we have questionnaires, but those are expert knowledge. People need to fill some forms for us to see what characteristic does this buildings or infrastructure have. But with the help of the computer vision, I mean, before the computer vision coming into place, no one was thinking about something like that would even be possible. But now we can just look at the street view images, we can look at the satellite images, and define such many characteristics and the features that, for example, this expert knowledge or tax data, census data cannot offer us. The same is for post-hazard damage assessment. So for example, when we have like a large hurricane or a big wildfire, I mean, what they're doing, traditionally, they're dispatching some experts to look at the buildings, go in front of the building, take some street view images from those buildings to assess how much the damage is, or actually helping to do the mitigation and also recovery stages. But now we can do that simply from satellite images. So if you look at the satellite images, you can see that we have buildings of different like damaged levels or severity. But, this is only something that computer vision can solve. And for example, say this is a very damaged building. This building is somehow damaged on the roof and the others. And the computer vision tools and the deep learning models are capable of that compared to using the expert knowledge. The other example is related to inspection and construction quality. So for example, on a larger scale, when we're thinking, like, for example, we have many buildings inside the California, and if you want to see how good they are, or for example, the dams and other infrastructures, some people should go there and take a look. Okay, here is a crack, here is the damage or not. But we can see that we can use the computer vision for inspection, for like monthly inspection or timely inspections, or for the construction quality also. For example, if you have for example, for the pavement, for the asphalt, we can use the AI to actually say how the construction quality is, or for example, how is the status of the road and the others. So it can completely do the expert knowledge job. The other civil engineering methods that the AI can help in, or the other branches, are physics-based models. So, for example, if you have a spring and if you have the force F, and we have the center at the X, we know that F equals kx. But what if you go to a very complex building? I mean, all these beams and columns are some sorts of nonlinear springs. So we can solve these problems, but these problems are generally solved by finite element methods, and they're very time consuming, especially if you're assuming some nonlinearity in the behavior of the materials. So the question is, can deep learning comes in here? I mean, deep learning doesn't understand anything from the physics of the building, but can it be used to generate data for us? And the results saying that yes. I mean, if you want to run the whole nonlinear time history analysis, that could take a long. So we use some more simpler methods like multi-degree of freedom simplifications. But the AI is shown to be even more robust and more exact than using simplification. So when we cannot do time history analysis, we can use the AI in its place. I know you heard something about like those models that generate 3D like words. I mean, if you give it a prompt, it would give you like a video or a short movie. And they're saying like that if the data is ample, if the data is enough, it's like that those models are understanding the physics of the problem. So here we cannot actually see that, but this is a very complex physical problem. So if it can generate very realistic responses for that, it means that it also understands some physics of the problem. The other example is the slope stability and the landslides. So this is again a very physical model. I mean, if we have the profile of the land, if we have the mass of the slope, we can use some finite difference methods by having the weight and the shear loads and the others to do the problem. But we also can do it with AI, and not just the slope, by using some GIS data, remote sensing data. And it is shown that if we somehow input those physics, I mean, the physical laws into the process of training those deep neural networks, it can even outperform those physical models, maybe in the prediction of the landslide susceptibility. So this is what this research is doing. So I'm gonna get back into my first slide. So for the civil engineering methods that were already been done by data-driven methods, I mean, the AI and the resurgence of the the emergence of the deep learning is truly dominating the field, because older models, newer models, so newer models are definitely better than older models. But what about the expert knowledge? I mean, the expert knowledge, if it comes to the computer vision, if, for example, some experts need to read something or see something, that's actually what the experts are doing. It's again shown that the AI is much better. I mean, because even if you look at two experts' idea on the same thing, there's a good chance that they won't be the same. And the AI gives us like better and more resilient, robust results. But for the physics-based model, I mean, the AI, I mean, because we are talking about the physics, if the physics model is perfect, then nothing can beat it. But the question is like that, can leveraging AI reduce the cost by maintaining some good level of performance? So this is the current research that is going on. And for any machine learning models, I mean, generalizability is the main concern. So if you have ample enough data, if you have a representative data set, and if you have good models, so for example, multi-layer perceptron cannot do what a transformer is doing for natural language processing. And if you have all these factors, I guess probably the civil engineering is dominated by AI models, and every day we are seeing some very great new results. Yeah, I would be happy to answer your question inside the chat and after the panelists finish their presentation. Thank you.
Thank you. So next one is Dr. Tsukasa Yoshinaga from Head and Neck Surgery.
Thank you. So My name is Tsukasa Yoshinaga, and I'm working in the Department of Head and Neck Surgery, and I would like to present the possibility of AI research in speech production, considering the clinical application for patients who have speech disorders or who need speech therapy. So when we consider the current application of AI in speech communication, speech synthesis and speech recognition are one of the most powerful usage of machine learning so far. And those are utilized in products like Siri, Alexa, and Google Home. And machine learning enabled to synthesize natural human speech using the large data set of human speech audio, and the naturalness was much improved from the previous models. However, inside of the machine learning is a black box, and the natural human speech synthesis does not mean that the model understood the mechanisms of actual human speech. So in the actual human speech, many kinds of physics are related to producing a wide variety of sounds from vowels to consonants. And each organ, like tongue and lips, move very fast to produce each sound. And if you consider people who have difficulty in speech, we need to know the mechanisms of the speech production to treat as a speech therapy. So when we consider the physics of speech production, many phenomena occur to produce one sound. First, we exhaust the air from the lung by elevating the diaphragm. Then the vocal folds located in your throat vibrate to produce the sound sources. The size and tension of the vocal fold influence the pitch and voice quality. And once you have irregular vocal fold shapes like vocal polyps or laryngeal cancer, the vocal folds cannot vibrate properly. Above the vocal folds, the tongue moves up and down by contracting the muscle fibers. There are 7 muscle fiber orientations, and the combination of muscle fiber contraction enables to deform in many variety of shapes. Finally, the sound produced in our mouth propagates from the lips to, and listener can recognize the sound. As described here, all phenomena can be modeled in a physical simulation to understand the mechanisms. In addition to that, we want to know what will happen when patients have irregular speech with diseases like vocal polyp or cancer. So in the current research project, we are trying to identify the potential contribution factors of unique human voices at a physiological level. As you can see in the left picture, there are many muscle fibers related to form the vocal folds in our throat. By considering the muscle fiber contractions around the vocal folds, we try to clarify how each muscle affects the vibration of the vocal folds and the sound generation of individual voices. However, one problem is that it still takes lots of time to simulate all phenomena in the current computational technology. So for this solution, AI can be used to predict the phenomena in a faster way. To describe the physical phenomena using the machine learning, the physics-informed neural network, also known as PINN, is proposed to solve the problem. The PIN can embed the knowledge of any physical laws that govern the given dataset in the machine learning process. So in this case, we can embed the physical laws like equation motion for vocal fold vibration or tongue movement, or we can also embed the Navier-Stokes equations for airflow and sound generation. And these equations can be used as a restriction for the learning process. If this learning process allows to model to perform calculation faster than the current simulation with enough accuracy, the AI can help us examine the state of speech disorders more quickly and more accurately, and the AI can be helpful in planning the treatment with doctors. Although I have not yet tried to construct this model, I believe that establishing such a model in future could help AI to treat speech disorders better way. Thank you for listening. This is the end of talk.
Thank you. So since I don't have any questions in the chat box right now, any questions from the
Yeah, maybe let me put it into the chat. I have one question to Barbara. Hello.
Yeah, go ahead.
Sure. I think you have an objective you want to optimize, and you want to do it in the latent space. And
Yes.
I'm wondering how can you make sure that it is consistent in the original in the optimization problem in your original space and the optimization problem in the latent space? How do you make sure they are consistent?
That's a good question, and we don't know yet what the latent space is going to look like. We're hoping that it would be low dimensional, but it could, I
Yes,
mean,
I know it's low dimension.
yeah, so hopefully it'll be low dimensional enough that will be a relatively simple manifold and that we can relate to. There's other people in my group that have done previous work on this. And you end up having relatively simple geometries. So we're hoping to be able to capture either like a cone shape or something like that so that we can achieve a minimum relatively easily. But I think it's going to be a little bit more complicated than that.
Yes, I believe.
Yeah. But thank you for the question.
Any other
Thank you.
people? If not, let me ask you, and it's a common question to everyone. Maybe just take a very short, brief answer. What are the major challenges in your field while using AI or machine learning or data sciences?
I can start. I think for me is the amount of data that we need to extract the models and managing all the amount of data, just not storing it, but being able to throw everything into a model is a little challenging.
What about computational power?
Yeah, we usually need to resort to GPUs, and hopefully we'll find a way to manage all the data. But I think right now, and at least in my field, is the main block on the road.
Thank you. Claire, want to?
Yeah, I think in addition to computational constraints similar to Barbara, our biggest challenge is validation. Wildfire smoke concentrations are really hard to validate relative to general air pollution because it's really hard to pick out source-specific contributions to emissions and downwind air pollution concentrations. So it's a challenge we're kind of facing across the board.
Thank you. Eulanca?
I think similarly to others, just kind of the amount of data that we have that we're able to parse through is also in terms of healthcare. I think training models to be more representative of the patient population that we treat. A lot of the times, the data that is used to develop, for example, the LLMs is a very skewed population, and so it does not necessarily apply to certain, underrepresented populations. And so making sure that that is a bit more equitable and more representative of the population as a whole.
Mojao?
Sure. Actually, as an applied mathematician, we are thinking in a different perspective. For us, we care more about the understanding of machine learning. Machine learning AI techniques have already have a lot of empirical success, but we want to try to explain it. And this is the challenge we are facing, probably different from all of you.
Good. Hesam?
Yeah, I mean, working with AI, probably the most difficult challenge is the data. So, for example, when we are doing some computer vision stuff, or maybe even when we are using like some LLM models, because those models were trained with like huge data, so we're not facing any generalizability challenges. We just need to fine tune them for our purpose with like few samples in a few shot learning or something, and that would work. But for example, when we want to work, for example, for the simulation of a nonlinear like response of a structure, or for example, for the structural monitoring, we actually need to produce some data. There are actually some laboratories, and on those laboratories, there are some scale structures. I mean, that's the biggest part of the problem. That's one. And also, because I was mainly in the civil engineering department. So, for example, when we're using some very heavy models to use, I mean, when I was using like Llama 2, I couldn't even work with more than 7 billion. For example, Barbara was talking, I guess, if I'm not wrong, and she's using like the Llama 3 or maybe Eulanca, sorry. And for me, I mean, if I wanted to work with Llama 2, I mean, there wasn't enough resources, for example, in the civil engineering department. I mean, now I'm in UCLA. I mean, we have some very strong computers, but I mean, from a civil engineering point of view, maybe the resources are not that much available to us, or I'm unaware of. So, I mean, that's also another challenge. I used to do many of my works with the Google Colab at the beginning, but the Google Colab is no longer like a good way of doing this. So we have to resort to some very strong, like GPU computers inside our group.
Thank you. Because
Sure.
Yes, so I also think that correcting the data is one of the most difficult challenges. Like if we think about the speech, we can record sound easily, but we cannot measure how the vocal folds vibrate or how the tongue is moving easily. So correcting the data that we cannot obtain easily cannot be modeled in the AI. So it is important to think how we need to measure the data and how we correct the data we cannot easily obtain in the current technology.
thank you. So I see the data and in some cases you mentioned about GPUs and the compute power. And I feel like this is the major problem across the board. One question Lisa mentioned in the chat. Do you want to come to Lisa? Do you want to come online?
Oh, sure. Thank you guys. Whoops. Thank you all for really, really interesting presentations. It was really great to see these. So you're answering my questions kind of in the chat, but I was just asking, what is it going to take for AI to just completely eclipse all other methods in your fields? And I see two answers already, but I'd love to hear from the others.
I can start. That's a good question. And in particular, I'm an aerospace engineer, but I specialize in fluid dynamics. And we have a problem. It's been a problem for decades. It's called the closure model. When we try to model turbulent flows, we don't have enough equations to actually have a system. Like we have more unknowns than equations. And so that means that we usually have to resort to very expensive simulations to solve the system in like very small steps to make sure that everything is continuous and we're being consistent with the governing equations. And so I think that AI is already taking over some of these more traditional methods in a way that, for example, there's methods called super resolution methods, so that instead of running a simulation that's very expensive that can take up months to run, you can sort of get a reduced order model of your system that will give you kind of the same result as one of these very expensive simulations in a fraction of the time. And so I think in a nutshell, what AI can do is extract all the relevant things in your turbulent system that will be able to somehow substitute all these traditional methods that are very expensive and maybe not necessary at some point. I hope that answers your question.
Yes, definitely. Thank you.
Anyone else want to take that?
I'll just add maybe less from a public health research perspective and more from a public health practice perspective, where there are state, regional, and county level departments of health and air quality agencies who are looking to operationalize air quality forecasts, for example, something Hesam mentioned. There's just a real lack of computing resource access in those fields. I mean, we struggle with it in research and academia, but it's something that our practice partners are absolutely struggling with. That would be a massive barrier to having AI sort of eclipse other less optimal methods.
Thank you. Anyone else?
Can I add one thing? So I think we need to have AI more accuracy, high accuracy, because now AI can achieve 95% accuracy, but it still has some errors, and sometimes that error can be really unphysical in the physical simulation. So that needs to be like, could be more like 99% accuracy. And then if the AI can show the error that follows more like physical way, then it will be more useful in our field.
Thank you. Any other questions from the participants? I know it's getting close to the time. If not, let's thank to all the panelists and all the participants for the wonderful presentation and insights into the AI in different fields and their own perspectives. We will have events year long, and next will be sometime in January. So hope you all will join again. And apart from that, I hope you have a good rest of the day and weekend. So thank you so much.
Thank you so much.
Yeah,
Thank you.
thank you.
Thank you.